Hello guys, welcome to our testing lecture. Today we are going to discuss the efficiency of algorithm. So it's covered in Computer Science 210. Let's get started. So the study goal today is what is time complexity and what are the types of time complexity and how efficiency can be improved. So, so when we talk about time complexity, efficiency, that kind of term. We can first relate them to the subject of physics. Like in physics, we have two kinds of efficiency. One is time efficiency, like just say with efficiency. Efficiency is like the ratio between uh, the work that you want to have divided by the total you have to cost. So this is efficiency. For time, efficiency is like more like distance displacement over time. It's like, oh, the total result is I have to complete uh, that far journey, like a journey of can say 100 miles, and how much time I cost. So I can get from here to there, 100 miles away. And the time efficiency is like 100 miles divided by the total time, like cost, say 2 hours or 1 hour, and then you can get the efficiency of your car, of your motion. And in real life, like same as our displacement over time cost, it's like can be used to show uh, on a single highway, on a single freeway, how fast the traffic flows can travel through this highway. And it can also show the efficiency can also show the highway's capacity or capability to have so many cars, have so many lanes and so many cars, so there's so many cars to pass through this point at a time. So, but for a single highway, like because we have rush hours, so sometimes maybe in the morning around 3, 4 a.m., like there are no cars out there. And for rush hours, like 5 p.m., 4 p.m., like we have traffic jam. So for a single highway, for a single part of highway, the capability or capacity of this highway is not changed. The changed thing is the amount of cars. The amount of cars enter the highway. So this is more like when you compare a highway as an compare a highway as an algorithm, and you want to set the point you enter the highway um, is your input where you want to input your data, and the place you want to get out from the highway is the output, where you get your output. And the things between these 2 points are kind of, we can compare it to be a kind of algorithm. And the amount of cars, we can compare them to the data we want to pass into the algorithm and to see how soon or how fast can we get the result back. Let's say, oh, I have 10 cars entering the highway, and I guess those cars can kind of like do speeding or something if there's vehicle, and you can get those cars to get out the highway to complete that far of the distance with a very short of time. But for large input, let's say, suppose you have a traffic jam, you're traveling at 4 p.m. on Monday, and you have traffic jam and traffic flows very, very slow. So because you have that big of input, let's say you have 1,000 cars or 10,000 cars on the same highway, and for these cars, you want them to travel from one point to another. Like it depends on the highway's capacity. If the highway's capacity is large enough, like say you are traveling on I-10 and you have 7 lanes, 6 lanes out there, so you can store that many cars. And maybe for some small highway, there are only maybe two. So, but I have the same amount of input. So it will also affect the time for the car from entering the highway to exiting the highway. So time cost inside we can call is like time complexity. And the cars we input is the cars on the highway, we can say that's the input amount. And the highway we can compare that into to be the algorithm. So let's say we want to pave a road so that we can reach somewhere, and we want to figure out the capacity of the road. So when we have a very large amount of cars on the road, so when I want to add more cars into the highway, will it be just be more crowded or be much more crowded or much more crowded? So it relates to the highway's capacity. And for programming, it relates to the time capacity, or let's say order of growth. So let's consider construction is a coding project, and the algorithm inside are different parts of the road. And we have to evaluate the efficiency of commuting. Yeah, we have to the efficiency of commuting. So for algorithm, if the input gets larger, and of course the number of operations will increase. Let's say I set my counter to 10 and I want to loop that many times, just 10 times. And let's say I want to input 1,000 into the counter, and the loop will input 1,000 times. So the input amount 1,000 will be having 990 operations. Then those you input with only 10. So number of operations will increase. So once you get your numbers of operations increase, suppose you spend the same amount of time of doing one operation, the efficiency will get lower because you have to do more operations. Yeah. So capacity and management of the road can be used to control the growth of the commute time. Yeah. So we have more lanes, so we may can manage the road well and control the road of the time spent on the road, because you can allow more cars to go past upon at the same time. So if you do that, even though your input will be larger, of course your order of growth must be your order must have to grow. But the growth can be mild, so it will not grow very dramatically. So if you do that, if you want to have a better management of your algorithm, so even though your input gets larger, the growth can be milder, so the efficiency can drop less dramatically. So you can just reduce a bit, but not too much. So when you run the Python program, so let's say, oh, I have bigger input. I have 10,000 cars on the road, and I have a smaller input. I have 10 cars on the road. So if you run a Python program in like an algorithm or function, it receives input. And then when you start running a Python function, the new frame will open. So if you consider oncoming traffic is the input of function, the commute time is the time spent to get a result. Let's say like, suppose allowing one car to go through upon takes the same time. So you're having 1,000 cars or 10,000, you spend more time than those who have only 10 cars. So because you have two operations, and at the same time, if you encounter some things like recursion, you have to open a new frame. So if you have to keep the frame opening, let's say maybe a single aggregate recursion or tail recursion, and that also takes some space and need the program to have some time to load them. So they will be also causing lower efficiency. So what kinds of time complexity we have there? Like as the input grows, we may grow very dramatically, we may go minor, and there are these situations we call different kinds of time complexity. Yeah. So we're going to introduce the types of time complexity. And the first thing is, just taking an example, like when I only have one car oncoming, so the input will be one. And when I call the function opens a new frame. So maybe example two, I may have 100. So this is like comparing smaller input and bigger input. Yeah. So from this point, you should know that for an algorithm, different different amount of input like will affect your time to execute your function, and it will take different duration of the time for you to wait for the answer to come out. So for smaller input, it surely have shorter time for you to get your results. And that also means your efficiency is very high. And meanwhile, if you're getting a very large input, so suppose for every operation, you have to take the same time to finish that. You get a greater duration of time for you to wait for the answer, and the efficiency will be lower. But we have different kinds of algorithm, and they react differently due to when they encounter some very big input. Yeah, and um, and we are going to talk about the complexity, which shows when different kinds of algorithm, like we divide algorithm into according to the time complexity. Time complexity is like when they are encountering big input, what's their time cost? Well, the growth of their time costs, like they are different. Some will increase time dramatically, some will increase time just gradually. Yeah. So we are going to talk about different kinds of algorithm and different kinds of time complexity. So I will use a big O notation to represent the efficiency. So, okay, scene one. So as more and more traffic coming, like this is the first type of time complexity. As more and more traffic coming, the commute time will remain the same, and the commute time will stop growing. This applies to all kinds of input, whether you are small input or maybe you are big input. Suppose I input one, and suppose I input 100, 1,000, 1,000,000, 1,000,000,000. The commute time will still remain the same. The commute time will not change. So the time is 100, 100, 100, 100. Like, and this time complexity, we call that big O of one, because um, because no matter how you change the amount of your input, they will do a fixed amount of operations onto your input. So that means whenever how long it will run, the frame will still be in initial. You will not open a new frame, or you may just keep one frame. You just keep one frame. Yeah, and you don't have to open new frames. So there will be no frames opening and no overlap operations. So any execute once, no matter how big the input amount is. So they can have the highest efficiency. Yeah. So the example of this is, for example, we can modify a list. Suppose our list.append1, and we can name a variable, name equals dvc. And we also have the print function, supposed to print hello world. Like maybe you have a function like input 1,000, but for print, if you don't use a while loop, it will just print once. And also tail recursion. Yeah. Oh, tail recursion is not. Yeah, sorry about that. Tail recursion is not. And you only use only if statement, like you don't have recursive call or something. And yeah, and you don't have while loop recursive code. You just have single some branching, some if statements. So if grade is greater or equal to 60, like for the whole thing, you just execute once. So this is O1. So we have 4 examples here. Yeah. So this is like no matter how big your input is, you will still remain the same, and you will not change the time for you to wait for the output. So the next one is called linear growth. Big O of n. It's like more and more traffic comes, aka as more and more input comes, the commute time will increase proportional to the input, proportional to how many cars on the road. So the time is growing linearly. Yeah. So it's growing, let's see, I have 100 and 100, 200, 200, 300, 300. So it will grow linearly. Like this is the easiest one of order of growth. Um, that means um, that means the commute time will be proportional to the traffic amount, and the feature is like the same amount of operations executed as many times as the input amount every time. I guess that means like if you input 100, if you input 100, it would be 100 times longer than when you input one. Yeah, because it will input proportional. On the graph, it will be um, an inclining straight line. So yeah, so this is linear. So the example of linear is a single while loop, or single for loop, or a single aggregate recursion or tail recursion with increment or decrement. Oh, I mean increment decrement here is like you plus equals 1 every time for the counter, or minus equals 1 every time. So, and also the counter must be an input. The counter must be an input. Or otherwise, if you for the while loop, if you set the counter as a fixed number, no matter you input 1 or 1,000, it will still be big O of 1, because the input does not change the number of operations. So for n and b, let's say n is the input. So while n is greater than 1, b will plus 1 each time upon 100, and n will decrease by 1 every time. So you will loop. So the n input is 100, and you will loop 100 times. If I plug in 1,000, you will loop 1,000 times. So the time cost is proportional to the input of the amount of your input. Yeah. So this is linear order. This is the linear growth. Yeah, linear growth with a big goal of n. And next one, as more and more traffic comes, the commute time is growing. It surely is growing, but it's more and more slowly. And then it will be convergent, or it will be constant um, at some certain amount, looks like. Or you will be very, very moving very, very, like increasing very, very slow. So I have example like total, you have 100, and I increase dramatically to 180. And then you go to 2, like for 100 to 180, the difference is 80. So from 180 to 220, the difference is 40, and difference is 20, and difference is 10. It's like it is increasing, but it is increasing a very slower rate of growth. So this is close. This is or is close to big O of algorithm n. Yeah, like for algorithm, we have a lot of base. It depends on the algorithm, but we all call them logarithm. Yeah. So this means it is growing, but is within a decreasing rate of growing. So the growth rate is still greater than 1. It's still greater than 0, but it will be decreasing. So for linear growth, the rate of growth is fixed. It is increasing, it is greater than 0, and it is fixed. It will not be changed. And for this one, the rate of growth will be decreasing, but still greater than 1. Then that will cause the time to be increased very dramatic um, at the beginning, and then it will slowly increasing. So it will not even the order with growth will not be as big as the order of growth for linear. So it means the same operator will be executed fewer times than the input amount. Suppose I input 100 and the number of operations will only be, I guess, maybe 90 or maybe 50. Sounds like that. Yeah. So the example of big O of logarithm. So it is like single iteration and recursion. But if you are having a number each time, so the worst case of big O of algorithm, so is algorithm of n. Like because for the graph, suppose this is a graph. Um, so wait, suppose this is the graph and this is time and this is input. So this is linear and this is algorithm. So for algorithm, it will surely smaller than the linear, uh, smaller, yeah, than the linear. But for some worst case, let's say if you are not having a number, kind of, if you are having a number and but having the result of having a number is the same as you decrease by 1, sounds like 2 to 1, and it will be same as the linear growth. Like it will be smaller, or maybe it will be equal. It will not be greater than the growth of linear. So maybe we can do having a number, and we can do like a number divided by 3. So having a number will cause in logarithm um, base 2 of n. If you are having a number divided by 3, it will be logarithm base 3 of n. Yeah. So this is also like if you say the difference of linear and algorithm on the code, you say because for algorithm we only for linear algorithm we only do like increase or decrease each time, which means the input will be the same as the number of operations. But for having a number, let's say, oh, if I input 100 and I will decrease to 50 for only one step. Um, so this will be only one numbers of operations for 100 to 50 in algorithm, in logarithm. But for linear algorithm, um, you will have to take 50 steps from 100 to 50 because we only decrease by 1 each time. For here, I'm having a number, so I'm decreasing a lot of numbers, of operations. So this is logarithm, and the next one is called quadratic order of growth. So as more and more traffic coming, the commute time is proportional to the square of the traffic amount. So looks like x squared. So it would be 100 and then 400, 900 until 10,000. Yeah. So it's increasing quadratically. So it looks like x to x squared diagram. So we call this growing and the big O of n squared. So how to cause order of growth of big O of n square. We are using nested loops. So for nested loops, suppose for here, I'm doing bubble sorting. Um, suppose like because for here I have two while loop, and for each while loop, it is nested. They one is nested in another one, and these two, the counters of the two while loop are all inputs. Are all inputs. Um, suppose okay, while A is the length of this, so because this is an input and the length of this is also an input, so while A is that input, like for shorter list, it will have a shorter amount of input, and for longer list, it will be a bigger time. It will be a bigger amount of input. So, um, so, like suppose I have five. So for the bigger loop, the outside loop, I have to loop total of five, and for the inside, each time, oh, um, for inside each time, I have to do for while. For while B is A, B is less than A. Suppose A is 5. Every time it become 1 to 5. So for 1, 2, 3, 4, 5. Uh, so every time B will be, so for here B will be only 1, and B for here will be 1 to 2. B will be 1 to 3, 1 to 4, 1 to 5. So for the same is the first one, if A is 1 and B will be only having 1. But when A goes to the second one, let's say 3, so B will travel through A to 3. We travel for 8, so 1 to 3, from the first one to the second one, and when I travel to the third one, let's say 2, so B will be becoming 1, 3, and 2. Travel through the first, second, and third place of the list. So until you travel for all the lists, and for the fourth place for A and B have to travel from the first to fourth place. It will take 4 steps, and for 5, B will take 5 steps as well. So this looks like 5 square of operation, like because for the these two while loop, these two while loop, the counters are all the inputs. Yeah, are all varying. Are all varying depends on your input. So when you have two counters, like in the nested while loop or for loop, if you have two counters that are all varying depends on the input. They are all related to the input. So they will have quadratic order of growth. It depends on how many nested loops in the algorithm. Like for here, I only have one nested loop inside another one, so there will be n squared. If I'm having 3, there will be n to the cube. If I'm having 4 while loop, it will be n to the 4th power. And yeah, and for another situation is that because for these two counters, the first counter, the second counter is related to the first counter. If the two counters are not related to each other, but they are both inputs. Let's say suppose while B is less than 100, maybe less than 4, B less than 4, and B will, if I set B as a new input, so there will be there will not be n times n. There will be n times mn. Suppose I set B equals to mn, so it will be n times mn order of growth. So I mean like for each step of the outside loop, the inside loop have to loop mn times. So I have to run the outer loop for n times. So each step in the outer loop, I have to loop mn times. So it will be n times mn. So the order of growth will be n times mn. Yeah. So it says quadratic or it's kind of like multiplication. So, and also depends on how many loops nested inside one another. So, okay. So next one, the last one, it is exponential. So, for exponential, is increasing the most dramatically. Yeah. So let's say start from 2, and this is 2 to the first power, and then 2 to the second power, and then 2 to the third, fourth, fifth, until all the way to 10th. I only take 10 steps, and I have reached from 2 to 1,000. If I'm doing linear, I have to take 1,000 steps to reach that amount. But for exponential, I only have to do 10 steps to reach that kind of amount. Let's say if we have 20, it have reached like 100, like 1 million, 1 million. That applies for big O of 2 to the nth power. For this order of growth is the most dramatically one. It runs and it has the number of operations the most dramatically. So it is very amazing, I think, and it is very horrible. Yeah, it is very because if you only have very small input and you get that many numbers of operations, when you're using that for big input, what will you do? I guess you cannot use this algorithm because once you use that, the, the computer will be likely to get sick because, oh, I can't do that. I have to do billions and billions of operations only for your 10,000 input. Input equals 10,000. So, um, so for scientists and programming, they are very likely to avoid having this order of growth because it would be very bad because they can only use that for smaller input. So the example of order growth is the tree recursion. Yeah, tree recursion. So so for so for exponential growth, let's say I have Fibonacci. So other than the base case, let's talk about the recursive step. So for recursive call, like because for this function, I have to, if I call this fifth function, I have to open one frame. And at the end of the fifth function, if number is not 1 or 2, I have to call another 2 function calls. I have to call another 2 recursive call. But at the same time, I didn't close this first Fibonacci function call because the last step for this recursion is the aggregation. I have to aggregate the results returning from Fibonacci of number -1, the first recursive call, and the second recursive call, like by uh, I say by applying recursive of or something. I have to wait for these 2 answers to come, and the last step, I have to combine the results so that I can eventually close the first frame. But for the so it will be like I only have 1 frame, but for this time I have another 2 frames. This is 1. 1 is 2 to the 0th power, and this 2 to the 1th power. So for a single frame, if it's not free, let's say if it's 100, so I have to open another new frame. So that applies to each of the recursive call. So this will be another frame, another frame. So there will be 4 frames. And if I still haven't reached the base case, I still have to open new frames without closing the previous old frames. Yeah, so I still keep opening this to the second. So still open. This time I increased to third power, 1, 2, 3, 4, to 8. And then I still having more. This time it will be 16. 16. Uh, fourth equals 16. So I will having more. This will be 32. So it is increasing very dramatic because we take like loading or keeping a old frame opening is also numbers of operations, and it will also cause low efficiency for the time complexity. So I guess this is the one we are trying to avoid. Yeah. So I guess we also have 2 to the nth power or something if you have 3 recursive calls, or maybe 4 to the nth power if you're having 4 recursive calls. So this is the biggest one, exponential. The smallest one is big O of 1. So we can have a small summation. So big O of 1, the type we call the constant order of growth. So the definition is like steps that taking the same steps will be the same regardless of input. I input 1 and I input 1,000, 10,000, 10 billion will be the same. And the example of that is to modify this. Yeah. And the goal of n is called linear. So the steps will be proportional or will be same of your input amount. Suppose I input 100, I have 100 order of operations. Suppose I have 50, I still have as input, I will have 50 of number of operations. And the example is that a loop of recursion with increment or decrement the input like is plus or minus 1 each time, or also this comprehension. And the logarithm is that I have to decrease the counter very dramatically. I'm not just going to minus 1, add 1, minus 1. I'm doing halving. I'm doing cutting it by half, cutting by 2/3, cutting it by 3/4 or something like that. So the number of operations will drop very dramatically as the amount of input gets very larger. Um, it is still increasing. It will not decrease, but it will be as the input gets larger, it will be much, much smaller than the linear type of time complexity. But for very small input, let's say 2, like having a number by 2, by 1 or by 2, having 2 by 2 and 2 minus 1 get the same result. So for this time, I have very small input. So logarithm will be likely same as the linear. Yeah, same as the linear. So for quadratic, I will have bubble sorting as example. So I have nested for loops or while loop, and their counters variant. Their variant depends on the input amount. If the counters are related to each other, like say the inner counter is related to outer counter, and they are dependent. The inner counter is dependent due to the outer counter, and this will be more likely to be n squared or n cubed and n fourth. Otherwise, if the two counters are all input and they are all independent to each other, so they will have n times m. They will have n times m for order of growth. And finally, I have exponential. So we have 2 to the nth, usually just 2 to the nth is less likely to have 3 to the nth. And you will have tree recursion because every time you open new frame, you have 2 recursive call, and 2 recursive call will still open 2 new frames for each recursive call, and then you will have 2 to the 0, 2 to the 1, 2 to the second power, and 2 to the third, 2 to the fourth power, and then it will go dramatically. Yeah. So efficiency, or let's say speed limit of a row. The speed limit will be the greatest for big O of 1 because I can allow any input of cars inside, so you can have as high speed as you can. It will decrease for logarithm, and then decrease for linear, and then quadratic, and then exponential. For co-loading amount, it is the opposite. For co-loading amount, the exponential one is the greatest. because you have to maybe open tens of thousands of friends for only maybe an input of 1,000. But meanwhile, for a big O of one, like regardless of the input amount, uh, so when you have very large code loading amount, it will be less likely for you to have a high efficiency. It will be more likely for you to have very low efficiency because it takes time to load the code. It takes time to do the numbers of operations. For yeah, so it takes more time to do greater, like for a bigger number of operations. Yeah. So another one is that let's use the example of the highway. So suppose on the same road, uh, like when I'm traveling through towns and through countryside, I will have different numbers of speed limit. I may have 35, I may have 65. So if I want to travel from the east side of this state to the west side of this state using this road, if I want to only have one constant speed, um, and I don't want to do speeding because I may get ticket from the police. So if I want to be safe from avoid getting ticket, so safe I in case I want to be safe and don't want to get tickets, and I want to run at a constant speed. So what speed do you think is appropriate? So I will choose 35 because for 35, um, because for 35, uh, it will because I have a part of road that only allow the maximum speed of 35. And for other roads, oh, I have higher speed limit. And that means that I can run safely at speed limit of 35. So if don't want to change the speed, or if I want to unify this the whole row with the same speed limit, I will use 35. Because if I use things like 45 or 65, if I go past this part of the road with only speed limit of 35, I may get danger because that road can only suitable for cars running under 35 mph. So that will cause danger. So if you want to unify the speed limit for the whole road, or if I want to run at a constant speed, I don't want to change speed, I'm running at a cruise control or something, and yeah, so um, you will not change your speed higher than 35, because if you're doing higher than 35, you have to change speed at this part. Yeah, so for programming is also the same. So if I want to determine the efficiency of one algorithm, I will have to analyze each part of the code to determine like because you may if you divide the code into several parts, you may have different results of the efficiency of algorithm. I suppose for the Fibonacci algorithm for this one. So as I said, like for if statement, if you do not have recursive call, it is just big O of one, just big O of one. And if I add in the while loop here, if I add in the while loop here, what is that? I will maybe having a big O of n as well. If I want to loop the number is smaller than 1, 0, and number minus equal 1 at this time. And I will also have a big O of m. But for the last part, I have two recursive call, and I'm having, of course, for this one, I'm having a big O of 2 to the nth power. So I have a conclusion that I have already discovered three kinds of order of growth in this algorithm. That is big O of 1, big O of n, and big O of 2 to the power of n. So which one do you think will be the eventually? I will say big O of 2 to the n. Because when you relate to the example I just talked about the speed limit, the speed limit of the big O of 2 to the n is the smallest one. And this is in medium, and this is the greatest one. I can allow any speed limit on the road. And this one, I may only allow 10, 25. This let's say maybe 35. So because this is an algorithm, and this is the things that you cannot divide when you think about the efficiency. Because when you run the algorithm, you will run the whole algorithm, not just a part of them. So um, you will think about the lowest speed limit, like for the part that causes you to have a very low efficiency, which is the big O of 2 to the nth power. Yeah. So for the algorithm here, although I have big O of 1 and big O of n, I will still have big O of 2 to the power n for my answer for the efficiency of this algorithm. So next one, optimization. So which recursion use memory method? I say tail recursion because tail recursion, when I say memory, is that you have to use some auxiliary variables. You have to use some new variables to store the result. Like say in recursion, in single aggregate recursion, we use recursive leap of faith to assume the function call returns an answer. But for tail recursion, I will do the opposite thing. I will when I run from at this when I run from n to 1 to n to 100, I will run step 1. I will say 1 first, and then for 2, I will have 2 times 1, and I will store 2 times 1 as the result. And then when it comes to 3, I will times 3 to the previous result. And each time I store the result until I accumulate that to 100. For single aggregate, it's like I have to find the base case first, and then I have to travel from 1 to 100 first, and make sure I have to travel from 100 to 1 first. I'll make sure 1 is the base case, and then I have to loop it back. Yeah, I have to accumulate them back. And for this part, when I want to accumulate back, it takes more space for you to load the frames, and for the computer to load and remember the frames. They are still opening. Yeah, but for tail recursion, I actually cut. Yeah, I actually every time I close a new frame, I will open a new frame. I will close an old frame. Yeah. So this is the one we use simple aggregate recursion, and this is the one we use tail recursion. So we can use variables to store some small results to reduce the loading amount. Yeah, to reduce the loading amount. So we can enhance the efficiency of algorithm. So because for opening a new frame, let's say actually tail recursion and single aggregate, I think they are both big O of n. But for computer, loading a new frame takes more, I guess takes more time, takes more space, and takes and have lower efficiency than opening one and while closing one, because you say, oh, keeping that much will make the computer having heavier task. So we can use some variables to store some small result and accumulate them every time. So we can enhance the efficiency of algorithm. So yeah, so the things the programmers do will rely, oh, I have to evaluate which efficiency of algorithm I'm having. Suppose I'm having this one, the worst one. So I want to increase the efficiency. I will go in at this way. I want to jump it to this one and to this one to reduce to enhance my efficiency. So meanwhile, you have to make sure that you're having a smaller amount of co-loading. Yeah, a smaller loading amount. So keeping an old frame will surely have a much greater loading amount than closing it while opening a new one, because when you close one and open one, Yeah. When you close one and open one, you will only have one frame you have to load. But while you open one, this is the old one, and this is the new one. So when you close one and open one, you only have one frame. When you open one and open another one, and open another new one, and you have two. And for this one, I will still close and open as it goes by, but I will still open, so I'll be free. So in the long run, I will have one frame for here every time, but you accumulate the number of frames. So you make your code, make your loading amount greater. So the thing is like, oh, you want to reduce the code loading. The thing to reduce is like to store the data into some variables. Yeah, to store the data into some variables and take the variable into a new function call into a new frame. So that will be better than just loading. It's optimizing. So the practice is like, oh, I have two examples of thinking about the efficiency, like say, what kinds of the what kinds of efficiency are there? What kinds of time complex of them? So um, so input is n and b is 0, and for while b is okay. So I have to loop b for 100 times. So each time I increase b by 1. So the step will take 100. So when you think about efficiency, while we have to be very careful because you have to think about whether the counter is related to your input. So for this one, oh, you might say, oh, there's only one value. So is that a big O of n? Is that big O of n? But for this one, oh, you will see B has nothing to do with the input n. Like they are not related. There are no relationship of assigning. If you want to know whether they are related, you will see if they assign one to another or if they compare one to another. They have neither one. They are neither comparing one to another nor assigning one to another. So they are having no relationships between. So that means every time I have different input, the while loop will still run 100 times. So suppose I input 1 because b is only less than 100 and b plus 1 each time. So the input will not affect the counter, will not affect how many times for while to loop, for the while loop to loop. So this is not big O of n, it is big O of 1. Big O of 1. So how about this one? So n b input 0 while n is greater than 0, while b is less than 100. So for this one, I have nested for loop. So as I say, nested for loop is likely to be big O of n squared. And does it true? For this one, we have to think about the two counters of the while loops. We have to think about whether both of them are related to the input, like are the counters related to the inputs. Maybe two counters, uh, they are both inputs, and maybe only one of them are inputs, or maybe neither of them are input, and maybe and also we have to think about whether they are uh independent to each other. If they are dependent to each other, it's likely to maybe n squared or something. But if not, maybe n times m. Yeah. So for this one, oh, while n is greater than 0. So this is the input. This is the input. So uh, so for here, it will be at least big O of n. At least big O of n. And is it also big O of n squared? And while b is less than 100. And you can see also the two counters have nothing to do with each other. So although like b is only less than 100 and n is not 100, like unless n is inputted as 100, yeah, and they have neither assignment to each other nor comparison to each other. So they have nothing to do with each other, and you also want to see, so they are not related. They're not related, and also you have to see whether the counter b is an input. So I guess B is not, because B has assigned to 0 no matter what the input. There's only one input, and this will be input will be n. So for B, B is equal to n, and each time I have to add it to um, add plus equal to 1. So for this, so while B is less than 100, like guess I less 1. So suppose I add the line here between these while loops, and each time for n, suppose n is 3. Suppose I have to run from 3 until 2 until 1. So for each step of the outer loop, for each execution of the outer loop, and the while loop inside have to run 100 times. For B is 100. Yeah. So for the second one is also 100. For the third one is also 100. So looping 100, looping 100 every time, no matter what inputs you can bring in. So I think the inner while loop has nothing to do with the input. So the input will not affect the number of operations for the inner while loop. Like if every time you run the outer while loop, you have to run 100 times for the inner while loop. So which means it's only big O of n. It's only big O of n. Yeah, because you can just take looping 100 times as one number of operations. And for the outer while loop, it is related to the input, and so it runs uh, the input, the amount of input is linear or the same as the number of operations. So it will be big O of n. It will be big O of n. I guess we can use things like AI or something. I just find one. So we can determine whether it's so unknown. Uh, maybe you can say as a function. Uh, yeah, it's big O of 1 for this time. It's big O of 1. Uh, how about this? Let's see. Yeah, it's big O of n. So, and within the loop, there's another while loop, iterate 100 times. Yeah, okay. So, yeah. So that's it for today's class. Thank you. And the next one is our last one. And we will talk about the language of SQL. Yeah, see you next week.